Welcome to Study Loop.
This is the answer to Chapter 22, problem number 2 from the Smith Organic Chemistry textbook. And this problem is asking us to draw all the resonance structures of an acid bromide, and then to talk about whether or not an acid bromide is more stable than a carboxylic acid due to resonance. And so, firstly, I've drawn these three resonance structures, as you can see here. Electrons and the movement of electrons are in blue. And I do apologize, it looks like I forgot an arrow. So to get from this second structure to the third structure, a pair of electrons would just add in there to form that double bond between the bromine and the carbon. So the thing to note about these three resonance structures, bromine is not very basic. Bromide ion is not very basic. And so this structure where the bromine is participating in a double bond and has a formal positive charge on it, contributes very little to the resonance structures. So remember that resonance structures should be viewed as not that each of these individual structures occurs and that the molecules flip back and forth between these three structures, but that the actual structure is some hybrid of these three structures. So there's not a total double bond between the carbon and oxygen, and there's not a total negative charge on the oxygen or a total positive charge on the carbon, etc. But rather that in actuality, all of the molecules of this molecule, sorry, I phrased that badly. All of these individual molecules of this type exist as a hybrid between these three structures. And so this third structure contributes very little. So the bromine is going to have very little positively charged character. The bond between the bromine and carbon will have very little double bond character. And this is because the bromine is not basic enough to hold the positive charge. And remember, we can define basicity in different ways. But basically, one way to think about it is the conjugate base of a strong acid is going to be a weak base. The conjugate base of a weak acid is going to be a strong base. So HBr, hydrobromic acid, is a very strong acid. And so we expect bromine to be a very weak base. And that's what we see here. Bromine is not very basic, so it can't really stabilize the structure in this way as it's drawn for the third resonance structure. And so that resonance structure contributes very little to this overall molecule. And so given the molecular template that I've drawn here, with Z standing in for the carboxylic acid derivative. So Z could be OH and it would be a carboxylic acid. It could be Cl and it would be an acid chloride. It could be NH2 and it would be an amide, etc. So in this case, we're looking at comparing when Z is OH for a carboxylic acid versus when Z is Br for an acid bromide. And so as we've said, bromine is a very weak base, but OH is a strong base. It's a very strong base. And so the text tells us that as the basicity of this Z group increases, the stability of the molecule increases. And so we expect the carboxylic acid, where Z equals OH, to be much stronger than the acid bromide, where Z equals Br, because OH is much more basic than Br. And so the problem specifically asks us to rationalize this in terms of pKa. And so I looked in Appendix A, and I didn't really find pKa values for an acid bromide. So we can't appeal to them directly numerically. But this answer is really addressing this in terms of pKa. pKa is telling you about acidity and basicity, and we're talking about OH being a stronger base than bromine, by a wide margin. And so we're not explicitly appealing to pKa. We're not citing numbers, but we are making this argument in the terms that the problem asked for. And so, again, just remember that when you have the molecule drawn like this, with Z standing in for whatever is attached to the carbonyl, as the basicity of Z increases, so does the stability of the molecule. And so that is the answer to chapter 22, problem number 2.